Welcome to the RocTunnel3 from Concept to Code webinar. And we're going to be taking you on a journey of the development of RocTunnel3. My name's Brent Corkum. I'm the Chief Technology Officer for Rocscience. I have over 30 years of software development experience in civil, mining, and geotechnical engineering. I'm joined today by Angela Lee, who's the project manager for RocTunnel3. And she's also the lead software developer on the project. And she'll be giving a nice demo at the end of the webinar. Now, the format of the webinar is that I'll be starting and I'll do a little bit of an introduction, and then Angela will take over, take us to the finish. Okay, a little bit about Rocscience. We're a world leader in developing innovative civil engineering, mining engineering, geotechnical engineering software. And what we're proud of most is the fact that we have excellent customer service and unparalleled technical expertise. Rocscience started about 25 years ago, and it's grown from a team of 4 people to 80 people. And we're situated in downtown Toronto, and we have over 10,000 users globally. Rocscience currently has 20 products with a range of different software, geotechnical software applications, both rock and soil. For instance, slide 2 and slide 3 are our slope stability products. RS2 and RS3 are our finite element products, which can do slope stability, retaining walls, tunneling, a number of geotechnical applications. RSLog is our borehole logging software, which just released a very innovative OCR tool, which allows for the conversion of historical borehole logs in paper form to digital form. We have settlement software, Settle3, Pile software, RS Pile. We're a leader in rockfall software, Rockfall 2 and Rockfall 3. We just released last year RockSlope 3, and now this year, RocTunnel3. This is a little diagram of the software ecosystem for Rocscience software, and it really highlights the integration that makes it extremely valuable to a customer of ours, that models can be shared amongst the different packages. And in particular, slide 2 and RS2 are well integrated. You can take a slide 2 model and export it to RS2, and with one button click, do a shear strength reduction analysis. On the right side, you'll see RockSlope and RocTunnel3 and how they're integrated not only with dips and S-wedge and unwedge, but they can also read slide 3 and RS3 models. So it's extremely easy to move models around between our particular software applications. The agenda of today is, first I'll present a brief history of wedge rock mechanics at Rocscience, and then what I'll do is talk a little bit about the inception and vision of RocTunnel3. What is RocTunnel3? Then we'll do some key features, and then a really nice demo of RocTunnel3 in action. So first, a brief history of block modeling at Rocscience. Over 30 years ago, we started working on block modeling, and in around 1990, we started to develop 2 particular packages, unwedge and S-wedge, and they were in DOS. They were done by 2 particular graduate students. S-wedge was done by Sandeep Shah. Unwedge was done by Bin Lee. And they were fairly simple vector-based programs. They both did tetrahedral wedges. S-wedge was principally, the math was copied out of the back of Everett Hook and John Bray's RockSlope engineering text. And unwedge was also copied from a paper that Everett Hook had written internally. So they were released in DOS, and then in about the mid 90s, they were converted to Windows, and at that point, we also changed the underlying engine to block theory, Goodman and Shea's block theory. And in about 2019, with the introduction of our M+ maintenance program, we started adding a variety of new features to each product, things like manufacturable libraries for unwedge, truncation surfaces. There were a number of things, and we sort of ran out of gas with what we could add to the two products, and that's when we decided that we would augment them into something like RocSlope3 and RocTunnel3. And RocSlope3 was released last year, and due to its popularity, we decided that we would do RocTunnel3, and it has just been released a month ago. Okay, a little bit about the inception of RocTunnel3. We often describe RocSlope3 as, what S-Wedge is to RocSlope3, unwedge is to RocTunnel3. And, we can think of S-Wedge and unwedge as local design tools. They're fairly simple in their geometry. S-Wedge is a simple slope. Unwedge is a simple extrusion of a cross-section of a tunnel or an underground excavation. And both of them have tetrahedral wedges only. When we moved to programs like RocSlope and RocTunnel, what we did was we now use full 3D geometries, the same types of geometry system that we have in our programs like Slide 3 and RS3. And we also introduced multi blocks with facets larger than the number in a tetrahedron 4. And we added in things like staging and all the bells and whistles that you need to have in order to do block analysis on real global scale. And that's what RocSlope3 and RocTunnel3 are. They're global scale analysis tools. Our vision is really to augment unwedge and S-Wedge. And let me state right now, by no means do RocTunnel and RocSlope replace unwedge and S-Wedge. Those two products, unwedge and S-Wedge, are industry standards. They're extremely useful local scale analysis tools with probability. They have DIPS integration. They have many different features. You can do models extremely quickly. But often now you want some idea of the global scale of block analysis, where all the failure is occurring, and in particular, the 3D nature of the failure. And you want to do risk assessment. And so we wanted to create something with an intuitive AI, something that would integrate with the rest of our software and use all the geometry tools that we've created in the past. Plus, we need to add facilities for obviously doing stageable excavations and backfill. We need stageable groundwater loading and supports. We need to be able to stage plots of results and that sort of thing. So there quite a lot here. So what is RocTunnel3? RocTunnel3 is a program that does structurally controlled failure. It's for rock. It's not for soil. Obviously, it needs joints, faults, bedding planes, folds, foliations, discontinuities of one form or another. One of the big things about these packages is in order to get a spatial representation of your failure, you now need some type of definition of where these joints are in space. And Angela will talk about that in the future and sort of define what you need to give the program. blocks themselves are analyzed for factor of safety, just like S-wedge and unwedge. They use 3D limit equilibrium method like S-wedge and unwedge, and they use block theory like S-wedge and unwedge, but to a larger scale. And RocTunnel3 in particular has staging, so it's really cool. You're able to stage the excavation and look at how that staging, how that successful removal of material affects what wedges are formed and when they're formed, which is really interesting. One of the first questions that I was asked when I was telling people that we were building RocTunnel3 was, can it finally properly model intersecting tunnels? For anybody that's done intersecting tunnels and unwedge, it's a bit of a kludge. You create a cross-section profile and extrude it down and accept the fact that it's a flat roof and that the extrusion length is a constant. No longer do you need to do that. You can have curved roofs. You can have multiple size tunnels intersecting. You can see blocks formed in the haunches, just not the roof and the side walls. And as a result, you can see a much better picture of the blocks that are forming near these intersecting tunnels. And of course, the reason why we're so interested in these areas of intersection is usually they represent areas where the span of an excavation is the largest, and thus you get larger critical wedges or blocks in these particular areas. What is the difference between unwedge and RocTunnel3? I mentioned a little bit about the geometry, but how about the joints themselves? In unwedge, there is no location. You assume the joints are ubiquitous, and you end up determining what the maximum size wedges are. And then you can scale the wedges down by a particular factor like persistence and that sort of thing. But it's really just one particular localized spot with one set of joints, and it's the maximum size joints. And it was really designed in a time when you really had no idea where the joints were in space. RocTunnel3, on the other hand, there is location as part of it. Blocks can be formed by more than 3 joint surfaces or discontinuity surfaces. You can have sequential removal of blocks, and so you get an unraveling of the blocks happening. There's all kinds of cool things that it does. Now, let me be clear here that, as I mentioned before, RocTunnel3 is not meant to replace unwedge. Unwedge does maximum size blocks. RocTunnel does not. So basically, you can't do the same analysis in both. Unwedge is really designed for a preliminary analysis. Because there's some idea of where the joints are in space, where the discontinuities are, you can get a picture of where the blocks that will fall out of the excavations will occur. And you get an idea of how big they are, what shape they are, how many sides do they have, all that sort of thing. You can get an idea of the spatial representation of factor of safety. You can get a spatial representation of probability of failure. You can go down a particular tunnel and get an idea as you walk down the tunnel, what is the change in factor of safety as you proceed. You can look at the changes by stage. You can identify key blocks. Key blocks are blocks in which, if they're removed, you can start an unraveling process. And then get some idea of support demand and rock bolting and shotcrete systems. And Angela will show a bit of this in itself. Go ahead, Angela.
Hi, everyone. As Brent mentioned, stage excavations are a crucial aspect of RocTunnel3. As the excavation is advanced, the number and shape of unstable blocks, and support demand can change due to increased exposure of fractures along the unsupported excavation face. And also at the same time, unstable blocks in previous stages may also no longer pose a risk if it's completely excavated away or then supported by backfilling. And since support demand is different in each stage, support design must also be carried out in a staged approach to ensure that blocks are stable across all stages. In RocTunnel3, the user can define one or more sequential stages, and in each stage, a geology volume can be assigned a material property, and that material property can also change from stage to stage. Volumes can be excavated. And finally, volumes which were previously excavated in a stage prior can be backfilled. Other entities such as groundwater, loading, and supports are also stageable in RocTunnel3. Material properties in RocTunnel3 are defined similarly to RocSlope3, with just the unit weight and groundwater conditions. Groundwater can be modeled by RU coefficient as some fraction of vertical earth pressure, water surfaces assuming hydrostatic pressure, or water pressure grids using interpolated pore pressure values. Note that rock mass strength parameters are not currently considered by RocTunnel3, since rock mass bridging or breakout is not modeled in this version. Multiple material regions can be modeled by delineating the external volume into smaller volumes, and things like borehole data can be used to stratify material layers automatically. Different groundwater conditions can also be assigned to each material in each stage. The geometry creation process typically involves first importing a surface or volume geometry of the ground in excavation. Most common 3D file formats such as OBJ and DXF are supported, and these geometries can also be exported from other Rocscience 3D programs such as Slide 3, RS3, EX3, RockSlope3, and Rockfall3, and then imported into RocTunnel3. Using built-in geometry tools to repair, simplify, or manipulate the geometry as needed, and then dividing the geometry into the required material and excavation subvolumes. And then the final step here is assigning material properties to the excavation. Material properties or to excavating the actual volume. And in the way that we tell RocTunnel that this is an excavation, we set it to no material. And the material assignments and excavations are stageable and assignable at each stage. We also need to define joint properties. Joint strength can be modeled by various shear strength models in RocTunnel3, and the shear strength parameters can also be optionally overridden by material to represent regions of weathering or gouge, for example. Waviness can be specified to model undulations in the joint surface to effectively increase the shear strength, and various water pressure options are available when modeling joints. For example, we can model them as dry, material dependent, which essentially just uses the groundwater conditions defined by material properties, water surfaces, water pressure grid, and uniform pressure. Joints in RocTunnel3 are modeled as surfaces with planar facets and defined by orientation, location, and size. Any number of major or minor structures can be added to the model. That data to model joints may come from sources such as scan lines and boreholes, photogrammetry and joint trace fitting, and even sample statistics of orientation, spacing, and persistence from DIPs. We offer 3 different ways to define joints in the program. The first one is measured joints, and these are modeled as circular disks with known orientation, location, and persistence. The dip direction, centroid, radius, and joint property is defined in this Excel-like spreadsheet. The data can also be directly imported from a CSV file or from a DIPS file. Synthetic joint sets are another way to define joints, and these are represented by parallel or near parallel circular disks with known distributions of orientation, spacing, and persistence sampled along a linear path. And that linear path could represent something like a scan line or a borehole, Orientation statistics can be sampled individually for dip and or dip direction, or using the Fisher distribution. Spacing can represent true orthogonal distances between joints or apparent distances along the linear path. Radius can also be sampled by a distribution. Note that a single realization is sampled to determine the centroid location, orientation, and radius for each joint in the synthetic joint set. Dip set statistics can be imported to define the synthetic set's sampling parameters for dip and dip direction using mean dip direction, and Fisher K values from the sampled set. The final way of defining joints in RocTunnel3 is the added joint surface. So one of the limitations of measured and synthetic joints is that they assume the joint surface is planar and circular in shape. And this is because often we don't know the actual shape of these discontinuities. And often for modeling measured and synthetic joints, radius is actually estimated by known persistence or estimations of trace length. However, if we do actually have the real surface or DFN geometry, we can import it from another source and set it as a joint surface. And these particular geometries are not limited to planar surfaces. Joints can also be trimmed to be contained within a specified volume or volumes. For example, jointing may vary by material type or spatially. Joints may not exist at all in certain regions, such as in overburden, soil, or grout. And once the joints are added, joint traces can be visualized for daylighting joints that intersect the excavation surface. And this provides us a good indication of the potential of block formation prior to computing the actual blocks. Optionally, external loading can be applied to the excavation surface as either point loads, line loads, or area loads. As well, seismic loading can be optionally modeled using the seismic coefficient. And again, loading is stageable and applied for a specified duration between the install and remove stage. Now, support design is a big part of an underground system. Any number of or combination of support types can be applied to stabilize blocks on the excavation surface. A uniform support pressure can be added to represent an average support capacity applied normal to the face. Spot bolts or bolt patterns can be added to anchor blocks into the rock mass. A uniform thickness of shotcrete can be added to provide shear resistance along the edges of the block and to prevent falling of smaller blocks, which oftentimes cannot be properly intersected by bolts. Similar to the loading, supports are also stageable and apply for a specified duration between the install and remove stage. A cool feature both in RocSlope3 and RocTunnel3 is successive failure. Now, beyond what we can see on the surface of the excavation and the blocks which are readily removable, we also need to understand the true extent of failure. As the blocks unravel, further instabilities are created in adjacent blocks due to newly exposed daylighting faces, which lead to more degrees of removability and unsupported faces. We also want to identify the key blocks that are actually controlling the overall stability. In a successive failure analysis in RocTunnel3, first, the blocks which daylight on the excavation are analyzed. Then any block with a calculated factor of safety less than the design factor of safety is considered failed and then removed. And these particular blocks are what we call the key blocks. In the next failure iteration, blocks adjacent to failed blocks are analyzed for their stability. These instabilities occur in succession, what we call failure iterations, and the analysis is carried out until no further block instabilities are detected. Results reporting in RocTunnel3, one of the options is to look at the block information, and essentially what this is a pane showing a full listing of each block's geometric removability, factor of safety, weight, volume, driving and resisting forces, sliding direction, failure mode, required support pressure, failure depth, and excavation face area. A a filter can be optionally placed on this data to query any of the columns, and only blocks meeting the filter criteria will be showed in this pane as well as in the 3D view. Sorting to the columns can also be applied. And all of this data can be easily exported to a CSV format for the current viewed stage or for all stages with the click of a button. If you require even more details for any selected block, we can also see the block in isolation and gather information about the joints that make up the block, joint intersections, and block vertices in the detailed block information pane. This, again, can all be exported to a CSV file. A graphical representation of the computed block information can be visualized by contouring the blocks by either factor of safety, weight, volume, driving force, resisting force, required support pressure, failure depth, excavation face area, failure iteration, and other parameters. And this essentially acts as a safety map, showing the locations and magnitudes for each stage. We are likely to see changes in computed metrics across stages, and these values are also plottable in a stage plot. So some values we may be interested in are perhaps block count across stages, sum of failed block weights, and maximum required support pressure, just to name a few. Now, in a deterministic analysis, inputs are assumed to be exactly known, and only a single realization of inputs is run to compute the factor of safety. To account for uncertainty in our inputs, a probabilistic analysis is available in RocTunnel3 and allows users to set material and joint property input distributions. Thousands of realizations for each input value are run to obtain a distribution of factors of safety for each block. Using the fraction of the number of failed blocks to the number of samples, we can obtain a probability of failure for each block. Probabilistic results can then be plotted on a histogram, cumulative, or scatter plot. Now, finally, it's time to see RocTunnel3 in action. For this particular demo, we'll review the geometry, which make up this 3-stage excavated model. We'll review the defined, measured, synthetic, and joint surface types of joints. We'll run a compute. We'll look at the safety map to identify the support demand of one of the stages. So in this demonstration, I'll just be showing stage 1 for the sake of time. And be implementing a support system consisting of shotcrete and bolts to achieve our target design factor of safety. And again, just for the sake of time, you'll notice that the model I'm using is already fully formed. I'll be skipping the geometry creation process in this demo, as we already have many resources to help users create and manipulate geometry, namely the previous webinar recording called Masterclass on 3D Model Creation with Slide 3 and RS3 posted on the Rocscience YouTube page. And just note, as Brent mentioned, Slide 3, RS3, Rocslope 3, and RocTunnel3 all share a common set of geometry tools and user flows for model creation. And as well, take a look at our tutorials posted on our website, which goes through the steps to import and create the model geometry. A good starting point would be the RocTunnel3 Quick Start tutorial. Now let's get into the demo model. The first thing to do in any start of the model creation process is to review project settings. In this case, I've already set them, so we'll just take a look at what I've inputted. For units, we're using metric stresses NPA. Under the stages tab, we'll note that there are 3 stages defined, and this allows us to excavate in 3 separate stages. Under the analysis tab, we have a design factor of safety of 1.5, and this is essentially our threshold for determining what is considered failed. Any computed factor of safety less than this value will be treated as a failed block. As well, this value is used to determine our required support pressure, as that support pressure represents what we need to add in terms of support capacity on average to the surface to be able to achieve our design factor of safety. You'll also note that I have successive failure turned on, which means that we are not only going to stop at what can come out in the first failure iteration, which essentially is everything that daylights and is immediately removable. In fact, we're going to go all the way back to the last failed block. And this really helps us later on in our support design. Now let's take a look at the material properties. Go to materials, define materials. So this is a very simple model with a single material property called rock, and we're using a unit weight of 0.026 meganewtons per meter cubic, and we have no groundwater defined. The geometry itself consists of a box, which defines our rock mass region, as well as junction 1, junction 2, and junction 3 volumes, which define our tunnel. Now let's review the material assignments in each stage. In stage 1, we see that junction 1 has been excavated, and if you note, the applied property in stage 1 is no material. And again, that just tells RocTunnel3 to treat this particular material region as excavated. And the excavation for junction 1 volume goes from stage 1 through stage 2 to stage 3. If we look at the stage 2 material assignments, we now see that junction 2 has been excavated. And if we go into stage 3, we see that junction 3 volume has been excavated. Now let's review the joint properties used to create this model. Go into joints, define joint properties. For this particular demo, I have 3 different material properties defined. You can define any number in your model. So I have a fractures more Coulomb property, I have a bedding more Coulomb property, and a fault more Coulomb property. And the only difference between these properties is a change in friction angle value. Now let's take a look at what forms the actual joint geometries. Let me just turn this off for better visibility. So starting off with the bedding joints. So you'll note that these are represented by near parallel, or actually in this case, exactly parallel planes. And I've created these joints using a synthetic joint set following a vertical path. So that could have been something from, say, a vertical borehole. And the reason why I chose a synthetic joint set to model the bedding is because I want to be able to easily create parallel surfaces which have some spacing distribution. So let's take a look at the inputs here. Going to edit. In the define synthetic joint properties dialog, we see that the applied joint property here was what we looked at before, which is the bedding more Coulomb property. The orientation is set to a dip and dip direction of 5 and 125 degrees. We have a radius of 100 meters. I just specified a value that was large enough so that these joints would extend through the entire model. And we have a mean spacing of 3 meters with an exponential distribution with a relative min of 1 meter and a relative max of 1.5 meters. The spacing option here is set to true spacing, which means that this is the actual perpendicular distance between each of these surfaces along the specified path. The next set of joints that we'll be modeling is the fractures. So these are modeled by measured joints. And if we take a look at the inputs for our measured joints, we can see that for each of these 53 entries, the dip direction, XYZ defining the centroid, and as well as the radius defining the size, are exactly known for each of these measurements. The joint property in this case is set to the fractures more Coulomb for all of these joints. And finally, we have our fault surface. And this fault surface is created from an imported plane geometry, which I then set as a joint surface using the joints and add joint surface option. So in this particular case, I've already set it as a joint surface with an applied joint property of the Baltimore Coulomb. And now finally, once we have our external geology as well as our excavation volumes defined and our joints, we are ready for a compute. To save us some time, I've already computed the results ahead of time. So I'll just turn off the visibility of these nodes we used to create the model, and we'll take a look at the results node. So the results we're looking at now are all of the valid blocks which can be formed based on the intersection of the joints we've defined along with our excavation volumes. So you'll note that as I toggle across stages, different blocks are potentially formed. Even more telling is if we look at removable blocks. So again, what a removable block means to RocTunnel3 and also RockSlope3 is that there is at least one valid direction in which this block can come out of its socket. So obviously, if we toggle again, we would see that as we advance the excavation, we see more possible removable blocks as we expose more excavation area. Now we can take a look at a subset of removable blocks, which are the failed blocks. And again, these are the blocks with computed factor of safety less than our specified design of 1.5. And failed blocks are essentially always going to be a subset of removable blocks, because if a block is not removable, it certainly can't fail. Let's take a look at the contouring. First, taking a look at the factor of safety. This is essentially our safety map showing us for our failed blocks, where are we seeing pretty much a near zero factor of safety. So you'll note that most of these are along the roof, which is very typical of underground excavations since they're fully unsupported, and most of their failure modes will be falling. But specifically when it comes down to support design, we need to take a look at other parameters other than just knowing that the factor of safety is not meeting our design. How do we get the information to design our supports? So one key parameter is to look at the required support pressure. And what the required support pressure value tells us is, again, this average pressure if applied normal to the surface, which will allow us to achieve our design factor of safety. And as I mentioned in the beginning, I'll be doing it for stage 1 only. So let's take a look at only the stage 1 results. And let's just note in the legend here that the maximum value is 0.07 approximately megapascals of required support pressure to ensure that all the blocks you see in stage 1 meet our design. Now, how this helps me with support design is, say, if I had a bolt pattern and I had on average a 1 by 1 meter spacing, this value is what I would need to ensure that my bolt capacity is providing. The second thing when it comes to bolt design is how long should this bolt be? And that's where we look at the second key parameter here, which is failure depth. And failure depth is a metric which is measured starting from the daylighting face of the block and projecting all the way back to the furthest failing block. And that may extend further than the daylighting block itself, because we need to keep in mind that in order for this support to provide adequate capacity, it needs to be actually anchored into competent rock mass. And note here that for this particular stage, the longest bolt length that we would require is something longer than about 4 meters. That's the maximum failure depth we see in stage 1. Now let's clear the results and start designing our support system. I'll turn off the visibility of each of these joints as well as the geology so we get a better visualization of the excavation itself. For my system, again, I will be designing a bolt pattern along with shotcrete. I've already done the pre-selections for the surfaces that I'll be applying support for, just for simplicity of this demo. So for my bolts, I will be applying it to the roof surface only. And this is to provide the adequate capacity to support these larger roof blocks that we saw earlier. So in order to do that, I have to select the surface first. So now it's selected in orange. Now I'll go to support, add bolts to selected surface. Let's review the bolt property we're using. I'm modeling this bolt with a simple bolt force. And what this means is that the engine will treat this as a simple force vector, not taking into account things like plate capacity, tensile capacity, and all these various capacities that other bolt types which are available in RocTunnel can model. This is a really good preliminary design type of bolt to model just because the assumptions are so simple. And we will assume a force application which is passive. And again, going back to our contouring of our blocks, we needed a capacity of the bolt of at least 0.07 meganewtons approximately if we were to do a 1-by-1 spacing. So in this case, this value should be sufficient. The orientation in which we'll apply it will be normal to the excavation face. And the length of 5 meters should be sufficient because, again, going back to our failure depth contours, we need something at least 4 meters long. For staging, we need to start the installation starting at stage 1 because the junction 1 volume is being excavated starting in stage 1. And we will never remove these supports to ensure that the capacity is provided throughout the entire duration while this volume is excavated. And then the application type we'll be doing is a bolt pattern. And we'll need to click twice to define the direction in which the bolt pattern is being applied. We'll click the button to just preview it to make sure that this is what we want to see. And again, the spacing I'm using here is 1-by-1 just for simplicity of the math. And once we're happy with it, click add to apply the bolts and done to close this dialog. Next, we'll be applying shotcrete to the walls and the roof. And this is to catch any falling smaller blocks which are not being properly intersected by bolts. So we'll make those selections. So you'll note that these are the faces I'm selecting. And again, we'll go back to the support menu and we'll select add shotcrete to selected surface. The shotcrete property I'm using has a shear strength of 1 megapascal, unit weight of 0.026 meganewton per meter cubic, and a thickness of 0.1 meters. And the staging will be the same as the bolts, where we apply it starting in stage 1 and we never remove it. Click OK to apply the shotcrete. Now that our support system is in place, let's recompute this model to ensure that our support design is sufficient to meet our design factor of safety for stage 1. Start with computing the blocks. And what the block engine is responsible for is intersecting the joint surfaces along with the excavation surface to find enclosed volumes which form our blocks. While that's going on, I can actually start reviewing some of these questions. So one of the first questions being asked is, you mentioned the option to apply shotcrete. Is there an option to apply mesh? There's no meshing option, but there is an option to apply a uniform support pressure. And we don't tell users what really this represents, but this could be something that you could convert to an equivalent to represent the capacity of something like a mesh or anything that's applied uniformly.
What?
Okay, so back to the demo. Once the blocks are computed, we don't actually know any information about removability or factors of safety, etc. So that's where compute kinematics comes in. And we'll note that what we're looking at in terms of results here are all of the failed blocks, and we don't see any. So that means that our support design was sufficient. And that's the end of this demo. Now, looking a little bit more into the future, Please note that all of the features covered in today's session are readily available in RocTunnel version 1, which is already released. But of course, there is so much more potential ahead. Looking into the future, we have stochastic discrete fracture networks in the roadmap, which includes, firstly, providing a simple DFN generator to create volumetric fractures based on orientation, persistence, and spacing or density distributions. And it's just like the one which is already in RS3, if any of you are familiar with that program already. And then secondly, being able to automatically generate and run multiple realizations of DFNs to create a distribution of block geometries in a probabilistic analysis. Thank you for all of your time. If you're interested in trying RocTunnel3, you can request a free trial through the Rocscience website using the link provided here.